Okay, so let's get started. So today we will cover the new chapter, the chapter 4, the classification. So classification is popular topic in machine learning. For example, the character recognition. We have the 10 categories. I mean, the maybe number recognition 0 to 9. If you work for the USPS and you would like to develop an algorithm to automatically detect the handwritten digits, then the classification models can be used. And also you have many other applications. Maybe the simplest one is binary classification of like patients, or even college admission, the binary classification of students in college admission, for example. And also there are some other examples such as ordered classification. For example, if you have the one ordered variable with 5 categories, for example, the teaching evaluation at college, the 1 to 5, and this is ordered, so certainly we have meaning of 1, 2, 3, 4, 5, but still it's not numeric in the sense that 5 is 2.5 times better than 2. So also the difference between category 1 and 2 and the difference between category 4 and 5 may not have the same meaning. So we are thinking about those categorical response variable. So that is classification. Okay, so before that, do you have any questions on homework or quizzes or previous lecture? Okay, so I will share the screen and to start chapter 4. I think the majority of them are in my 6840 class, maybe 1, 2, 3. I think the Victoria and the Nathan and the Thomas and the Hunter, maybe not majority, maybe half of them are in that class. So maybe there's some duplication of materials. But I would like to discuss logistic regression first. Then after that, we discuss some other models. Yeah, so chapter 4 classification. And we have several things to discuss in chapter 4. So at first, that we do some overview of classification. So the one simple example and the some other applications in a real world. Then we go to logistic regression. So at first we do the binary classification, the usual logistic regression. And next we consider the multinomial logistic regression. So that is for more than 2 categories. And also we discuss the ordered logistic regression a little bit. So for example, how to explain the ordered variables such as the rating of the 5 levels. And next we discuss the linear discriminant analysis. So linear discriminant analysis, basically we can do multi-category classification. Multi-category classification. So not much difference between binary classification and the 3 or more classes. And the quadratic discriminant analysis is also similar to linear discriminant analysis, but a little more complicated in terms of parameter space. And the last one is the k-nearest neighborhoods method. So this is more data-oriented method. And also it does not really matter whether the response variable is binary or has more than 2 categories. So basically, the first several ones are more flexible. No, the other way around. So the simpler, and the last ones are the more complicated but more flexible. So we have to balance the between these two, and also some strengths and the weakness in models such as logistic regression versus the linear discriminant analysis. So we will discuss that also. Yeah, so logistic regression is covered if you took my 5030. Maybe other instructors may not cover. And the multinomial logistic regression, I think I covered in 6840, not 5030, but except for that, not really. Linear discriminant analysis, I forgot, maybe it's covered in 6840, maybe not. Quadratic discriminant analysis, maybe not, and so on. K-nearest neighborhood has not been discussed in any other courses, I think. And I don't know, how many of you have heard of at first, maybe logistic regression, probably you have heard of it, right? And maybe linear discriminant analysis, LDA, how many of you have heard of it? Maybe 1, 2. How about quadratic discriminant analysis? 1, 2, maybe. K-nearest neighborhood, we have already discussed some in the previous chapters. Okay, so at first overview, we are dealing with these kind of problems. So first, for example, the categorize handwritten digits into classes of 0 to 9, and categorize the 150 flowers into 3 species based on measurements such as flowers diameter. So famous iris dataset have 3 species of iris, and then we have measurement of the petal length, petal width, and the sepal length and sepal width. And basically based on those 4 measurements, almost we can perfectly separate 150 iris. And another one, maybe simpler, but judge whether or not the patients are malignant or benign based on several medical measurements. So that is a very typical question in diagnostic medicine. So I did tons of analysis for medical doctors for this. So certainly it's useful in the medical applications. Okay, so this is one example. So the default dataset, this is actually in ISLR package, the package developed by the authors of this textbook. And basically, we have 10,000 consumers data, and we have several variables. The one is the income of individuals and the credit card balance of those individuals. And we have the 2 classes. The blue is not in default and red is in default. This default status may be, the 1 year later than the other data variables are collected. I'm not exactly sure about the specification, but we want to see what kind of customers will be in default in the next certain time period. And the blue is not in default and red is in default. So you can see some tendency. Actually, the income does not really matter. That's kind of surprising, but the balance really matters for default status. So if the balance is larger, the more people are in default. Yeah, of course. For example, if the balance is 0, then you cannot default. So yeah, so first thing we can do is, okay, so this scatter plot, and also you can see these marginal distributions. So if we see the balance by default status, then actually the people who have defaulted have larger balance, maybe a certain period before their default. But the income level, that does not really matter for the default status. Yeah, so that is the one thing. And now we think about the fitting the regression model for this. And obviously, the response is either the in default or not in default. So we can say, suppose the default is 1 and not in default is 0. Then what the situation look like? So for example, just for simplicity, we have just one X predictor, maybe balance. And Y is the default status. Default is 1. Then only possible Y values are 1 or 0. So the observations are probably like this. So many people with smaller balance are not in default, but if the balance get larger and larger, and more people are in default. So maybe some more observation here. Maybe in between both cases like this. But basically more observations, maybe even smaller balance, some people defaults. So like this. So, okay, so one way is, okay, so to fit the linear regression, so what happens? Okay, so this is fitted line, for example, because we have more observations around here, more observations around here. But this is obviously a problem. For example, what's the fitted value at 2800 in this graph? Then fitted value is maybe 1.3. That does not make sense because we know that the response is either 0 or 1. So 1.3 makes the error size of either negative 1.3 or negative 0.3. So that isn't good. It's just we can randomly say 0.5 or something. Then it's much better in terms of the distance from the actual observation. And even we just say it's 1. The 1 is the largest possible reasonable guess for the is the default status if the this is the value is 0 or 1. So the linear regression does not really matter, does not really works. And also, if we see the error distribution, it's far from normal, and even it does not have mean 0. If the predicted value is 1.3, it implies the error size, I mean residual size, is either negative 0.3 or negative 1.3. It can take only 2 values. So it does not make any sense. So okay, so still, you can fit it as an algorithm, but it isn't really a good idea, and it isn't logical either. So we have to use different method to fit this situation. And one good thing is, since we only have 2 values here, we only have a binary response. So we have 2 values. So 2 values are always ordered, right? So we can just define the order. So in this case, default is 1. So that's larger than the not in default, that is 0. If we have the 3 categories, for example, the blood type A and B and AB and O, we may not be able to order those 4 categories, or just the horse, the deer, and the giraffes. We cannot really order those 3 animals, but if only 2, always we can order. So in some sense, it's easier to deal with. Yeah, but so we need something more than linear regression. Yeah. And yeah, so basically essentially we need the probability of the person is in default. So yeah, so that is our idea to do the binomial classification and even the multinomial classification, but we will discuss it later. Yeah, so I would say that the binary classification problems are different from continuous response model, but they can be fitted as a regression model, because if we only have the two categories, always we can order these two categories. And it is hard to apply a regression model to a classification problem if there are three or more categories and there is no presumed order. If the three categories are ordered, such as rating, or, then it makes some sense to fit a regression model. But otherwise, we have to do something else. Still, a regression analysis is possibly fitted for each pair of categories. But that is very indirect method. Yeah. And also, even if there is an order for categories, it is not easy to see how to quantify the results. So suppose that the rating of movies has 1 to 5 scale, but the distance between rating 1 and 2 are not necessarily the same as the distance between 2 and 3. Yeah, so that is the case. Right? So if we have the 3 categories like A, B, C, we are not really sure about the order. Right? So usually we don't have any order. Okay, so any questions so far? Okay. So logistic regression. Oh yeah, sure.
Yeah, actually, you scroll up to the previous slide, actually. Yeah, so I'm just wondering. So let's say we did want to apply a regression model to a classification problem with 3 or more categories, and let's say that well, actually, I take that back. Actually, I guess my question would be, how come forming all possible pairs of each category when there's no order to the categories might lend itself more naturally to a regression problem instead of not pairing the categories? I'm not sure what the motivation for pairing the categories before you would want to do a regression analysis would be if there's no order in the categories.
So some models, some machine learning models are very complicated, and we almost have no hope to generalize it into multi-category models. So in such a case, sometimes the people, are forced to use the model for each pair of categories. So that happens for example, the support vector machine. So support vector machine is known as a good classification algorithm for binary classification problems. But actually, the extension to the multinomial models are really hard, and it's almost impossible. I cannot really explain in one word, but the classification problem itself is very complicated. So there is almost no hope. So, and I think that some researchers do pairwise comparison of those categories. If we use those decision rules sequentially, maybe we can do some kind of multinomial classification. Yeah, so that is one thing. So usually we don't have any hope. So if possible, we should avoid each pair of categories. So pair of categories are too complicated, right? Because suppose we have 3 categories and we have the 2 predictor space, x1 and x2. And okay, so category 1, maybe A is like this and B is like this and C is like this. These are typical realizations of x1 and x2 for 3 categories. Then we need the separating line between A and B, B and C, and B. So suppose A and C are separated by this, like this, and A and B are separated by this, and B and C are separated by this, then still it's not clear that this area belongs to what. So this area, if you compare A and C, it's more likely to be C, right? So in this area, so C is more likely than A. And also the C is more likely than B. this may be fine. C is more likely than A and C is more likely than B. Then it's fine. So this area may be fine. Maybe then this area is probably belongs to C. But you can see that, for example, A, B, B, C, here, maybe here. So this area, C is more likely than A, and C is more likely than B. But if you compare A and no, C, yeah, sorry, I'm so confused. The C is more likely than B, C is more likely than A. Yeah, this is fine. This is fine. I think A is more likely than C. C, B. Oh, sorry. I forgot. I made a mistake. So okay. So this area, actually, at first compare A and B. Then this is A and this is B by the definition of the separating line. So this is the B. In this area, B is more likely than A. And also, this is C and B separating this line separating B and C. So the C is more likely than B. But if we compare A and C, actually this is C and A. So A is more likely than C. So we cannot really decide which categories that this point belongs to. So actually, this is really a bad idea for classification. But if this kind of area is small, still we can use the pairwise comparison. So the motivation is, so if pairwise comparison is, some model is really excellent in pairwise comparison. If we combine those, possibly we can get a good algorithm. So that is the motivation. But generally, it's not really a good idea.
Gotcha. Thank you. I see what you're saying with that picture. That picture is very useful.
Yeah. Sorry. I cannot explain maybe clearly, but yeah. Do you have any questions? Other questions? Yeah. So the idea of logistic regression first. So suppose that the response variable is binary and X is some predictor value, either quantitative or qualitative. Then basically the idea is to find probability of Y is equal to 1 given X value. So that is the idea of logistic regression. So one reason is probability ranges from 0 to 1. Right, so probability is continuous. So it's a kind of similar to continuous response variable. So that is the one thing. If we treat logistic regression response variable, just the 0-1 variables, the 0-1 values, I think it's harder to deal with in the regression framework, but the probability is continuous, so it's good. That is one thing. Yeah, so that is the basic idea. Yeah, also, yeah, also, yeah, I think it's related, but if we use just 0 and 1, we cannot really determine the simple, error distribution. So in linear regression, we can assume that Y is equal to A plus BX plus epsilon, and epsilon is normal 0 sigma square or something. But even it's harder to assume expectation is 0 and also normal. So these assumptions cannot be made for binary response. So that is our motivation. And okay, so linear regression, logistic response is in R in linear regression. And logistic regression 0-1. But if we use the closed interval, so this is not, homeomorphic. So we don't have 1-to-1 map, the continuous 1-to-1 map from R to 0-1, closed interval 0-1. So that is problematic. That is problematic. So that we use the open interval 0-1. And this is a kind of, consistent with the statistics idea. So nothing is, has probability 0 or 1. in usual linear regression, suppose the y is far away from a plus bx, epsilon is very large in absolute value, but still it's possible with small probability. So basically, so this setting is actually most consistent with the linear regression idea. Yeah, so basically, okay, so we go to the this slide first. So this is the conceptual, the graphs, and the left-hand side is just what happens when we fit the usual linear regression for binary response variable, and this blue fitted line makes poor sense. And the left-hand side is the logistic regression. So we basically consider the probability. So we focus on specific range, for example, here. Okay. Then we have the proportion of the default and not in default. And you can see in this range, probably about 80% of observations are in default. So actually this value is about 0.8. So probability. So therefore, each value of the predictor variable, we can estimate the probability of default, not exactly this number. So that is the idea of logistic regression. Okay, so just some more details. So logistic regression, suppose for simplicity, the X is just a single predictor, and then the logistic regression formulates the probability as this. So probability of y is equal to 1 given X. So this is represented by P of X. So this is formulated by F of beta naught plus beta 1 X. So beta naught and beta 1 are parameters as usual. And F is a fixed function. This is called logistic function. And F of A is e to the power A over 1 plus e to the power A. And F is defined for all real numbers. Sorry, this comma should be here. And F is called a logistic function or a logit function. Yeah, F is from the real numbers, entire real numbers to open interval 0, 1. So the difference between linear regression and logistic regression is the existence of this F. That is one thing. And also another difference is we don't have epsilon. So we don't have this one. But the probability is a kind of expectation, right? So probability of y is equal to 1 given x is actually the same as expectation of y given x. Right. So expectation is always constant and no error terms. So even linear regression, we have y is equal to a plus bx plus epsilon. If we take expectation, e of y is equal to a plus bx. So it's a kind of natural that we don't have error term here. Yeah. So again, the f is one characteristic of logistic regression, and the no error term is another characteristic. But the no error term is in some sense the same as linear regression, since we have taken expectation already. And this is a graph of logistic function. So you can see it's centered at 0. And it's symmetric around this origin. And okay, so this is 0.5. Value is 0.5. And it goes to 1 as x goes to infinity, and it goes to negative 0 as x goes to negative infinity. And the slope is largest here. Yeah. Yeah, so that's the logistic curve. Okay, so now that we think about the some data example. So again, the default data set is in library ISLR. So maybe I should put it to make it reproducible. So 10,000 observations and the 4 variables. So default status and the whether or not the person is student and the balance and income. So we want to estimate the probability of default for each person given their balance. So balance is the most important factor here based on descriptive statistics. Student data, we haven't seen it yet. So basically, we want to do this kind of thing. So the balance is the predictor and the probability of default is response. So we want to do this. Yeah. And okay, so we have this formula. The probability of y is equal to 1 is f of beta naught plus beta 1 x. And the f of a is e to the power a over 1 plus e to the power a. So we can write in this way. Or some people prefer the notation, the expression of 1 over 1 plus e to the power negative beta naught minus beta 1x. Obviously, this is simpler, only 1 beta naught and beta 1. But since the sign is negative on the exponent of e, some people still prefer this one. For example, beta naught get larger, probability gets larger in right. So in some sense, this is more intuitive. So, but another expression is this. Okay, now we think about the inverse function. What's inverse of p? Sorry, maybe I would say inverse of f, maybe. Yeah, so what's the inverse? And sorry, maybe that is not a good way to say it here. So we think about what's the meaning of beta naught and beta 1 here. So since we have f here, it's a little bit harder to imagine what beta naught and beta 1 means. In linear regression, the interpretation is simple. So beta 1 is 2, then x gets larger by 1, then the y gets larger by 2. So it's easier to interpret. But the logistic regression, it's a little bit hard. So larger beta 1, I mean, maybe positive beta 1, I would say. Positive beta 1 means larger x implies larger probability. So we have some weak relationship between the y and x, but it's not clear what exactly beta 1 means. So we want to interpret that. And okay, so we transformed this function. So how to do that? Okay, so this is ad hoc, but we think about p of x over 1 minus p of x. Then 1 minus p of x is equal to 1 minus. So this is 1 over 1 plus e to the power beta naught plus beta 1x, right? So then px over 1 minus p of x, then denominators are the same here. This one and this one are the same. So this becomes e to the power beta naught plus beta 1x. Then take logarithm of both sides, then we get this. So now it's easier to interpret beta 1 or beta naught here. So suppose beta 1 is 2, beta 1 is 2 and x gets larger by 1. Then basically left-hand side gets larger by 2. Right? And what's the left-hand side? P of x is basically the probability of 1. So a kind of success probability if y is equal to 1 is success. So that is statistical so probability of success. And the denominator is probability of failure because this is 1 minus probability of failure. And probability of success over probability of failure, that is called the odds in usual English. And so log odds is the left-hand side. So we can see that the beta 1 determines the change of log odds. So x gets larger by 1, log odds gets larger by 2. So that is basically the best possible, the verbal explanation of beta 1. Yeah, and actually the g of y, that is the function of log of y over 1 minus y. So this is the inverse function of logit function or logistic function. So we say this is an inverse logit or inverse logistic function. So not many functions have inverse, at least. I mean, maybe the one-to-one monotone function has the inverse, but the no analytical forms often. But here, the both f and g, I mean f and f inverse are simple analytical functions. So this is good. So this is one reason that the people use logistic function for binary classification. Yeah. So that's the basic idea of logistic regression. Any questions so far? And I would like to ask you if you have already studied maximum likelihood or not. How many of you have studied maximum likelihood? Not yet. Yes, yes, no. I guess the Thomas should have learned already, yeah, because you took many courses. Okay, but okay, at least maybe some of you are not. So I would explain the idea of maximum likelihood method. So maximum likelihood method is the general idea of estimation. And actually the least square estimator for linear models, that is a special case of maximum likelihood method. So if you understand maximum likelihood methods, then you can understand better in some applications, some extensions of linear models. And actually the logistic regression also is based on the maximum likelihood estimation. So to estimate beta naught and the beta 1, so these are, so we use the maximum likelihood method. So idea is here. So consider the situation to randomly pick up a die out of 3 unfair dice, X, Y, and Z. And X and Y and Z are characterized by these probabilities. So all 3 dice are 6-faced dice, but the X is a fair die, and the Y and Z are kind of loaded dice. And dice Y, the 1 is more likely to happen than others, though the 1 will occur with probability 1/2, but the other probabilities are all 1/10. Okay. And the die Z is also a loaded die, and the 2 is most likely outcome for this die. And the 1 is next more likely, so 30%, 50%, and 30%. And the others have very small probabilities. And suppose you don't know which die you choose, but you can observe the result once. Okay. So, and suppose you pick up one of these dice and the outcome is 2. So 2 occurs for that experiment. Then which die is most likely? Okay, so we don't know which die we picked up, but if we compare these probabilities, you can see the Z gives largest probability for 2. So we guess that probably that die is Z. Okay. So, if you have picked up Y, then we have very unlikely to get 2, but we have already got 2. So, Z is most likely. So that is, often our, the principle for decision, right? So the die Z is the most likely. So our estimate is Z. So that is most likelihood. So the likelihood method. So maximum likelihood method or maximum likelihood estimator. So our estimate is Z. And this is actually the new idea. If you only studied probability theory. So probability theory, basically we have probability space. So die X has its own world, and the total probability is 1. And die Y also has a probability space, and total probability is 1, and this. So, but we see this table, vertically, not horizontally. So if we see this horizontally, that is just probability theory. We have 3 different probability space. But we use this table vertically. We just take this section. So that is a kind of new idea. And we compare these 3 values. So in this case, we have only 3 possible values, X, Y, and Z. And the probability is the 1/6, and 1/10, and 1/2. But in real example, so this parameter space, maybe I would say what? Maybe W. So this is sometimes continuous scale variable. So in such a case, estimate is also in a continuous scale. But the idea is basically the same, so that we choose the number which gives highest probability. And that isn't just probability theory, because we are comparing numbers vertically, not horizontally. Yeah, so this is the idea of maximum likelihood method. So, okay, so going back to logistic regression, we want to estimate beta naught and beta 1. So here, the pair of beta naught and beta 1 take any point on the 2-dimensional plane. So we want to find the best pair of beta naught and beta 1. And to find those values, that we can use maximum likelihood method. So suppose we observe x1, y1 to xn, yn. So here, maybe just simply we think about x is just the univariate, so just a number. And y is either 0 or 1. Then likelihood of beta naught beta 1 is defined as this right-hand side. So here the product over all observations with yi is equal to 1, and this is product over all observation over yj is equal to 0. So okay, so given beta naught and beta 1, that we can calculate probability, so that we have observations, maybe 1, 2, 3, and the probability of y is equal to 1 is estimated. For example, the 0.8 and the 0.2 and the 0.6. And actual y is observed here. So actual y is observed as, for example, the 1 and 0 and 0. Okay, what's the likelihood of this this data set with 3 observations? So at first, think about this observation, and actually the probability of y is equal to 1 is 0.8. So in this case, the likelihood is 0.8. Maybe I would say that yeah. So I need a little more space. So likelihood. And next one, okay, so our probability of y is equal to 1 is 0.2, but actually y is 0. But our probability of y is equal to 1 is 0.2. That means probability of y is equal to 0 is 0.8. So here, the likelihood is 0.8. And the last observation, so the y is equal to 1. Probability of y is equal to 1 is 0.6, but actually y is equal to 0. Probability of y is equal to 0 is 1 minus 0.6. So 0.4 is the likelihood, so 0.4. And we assume that observations are independent in our regression models. So we take the product of this. So that is the likelihood of entire data set. So in this case, likelihood is 0.8 times 0.8 times 0.4. So that is 0.64 times 0.4. So that is the 24. So 0.256. So that is our likelihood, entire likelihood. So just this formula that describes in more, the abstract way. So if yi is equal to 1, just we multiply p of xi. If the yj is equal to 0, then we multiply the 1 minus p of xj, because this is the probability of yi is equal to 1, and this is probability of yj is equal to 0. Okay. And yes, then in logistic regression, the p of yi is equal to 1 is here, right? And the p of yj is equal to 0 is here. So this is a function of beta naught and beta 1. So given beta naught and beta 1, we can calculate the likelihood. So now it's the same situation as the previous example. So we choose beta naught and beta 1 to maximize this quantity. So that is our maximum likelihood estimate for beta naught and beta 1. Any questions? Yeah. So in principle, I think that all of you understood this. And the estimation is more complicated than linear regression. So linear regression, we minimize the sum of squared errors, but that is actually just the quadratic function of beta naught and beta 1. So just we can do some linear algebra to solve it. But here, more nonlinear function. So we need more numerical methods to optimize parameters. So to get beta naught hat and beta 1 hat.
I do have a question. I just wanted
sure.
The population space is for this is just 8 cases, right? Or is this considered a well, it can't be continuous. It's 8 cases. Each 1, 2, 3 each, or 3 raised to the 2. No, 2 raised to the 3. Correct.
So 2
raised to the 3.
2 raised.
I'm looking at the population space. It would be
okay.
Total of 8 cases.
8 cases. Okay.
I'm just want to say if you were looking at trying to plot the whole thing, there'd be 8 cases.
8 cases? No, we are thinking about n cases. I'm not sure where 8 comes from.
I is equal to 1 or 2 or 3. Oh, this is.
This is just one example, but in general we have n cases, right? Yeah.
Oh, I understood the n cases. I'm looking at this one, and I was just thinking whether. Okay, it just continues on. Never mind. Thank you.
Okay, sure. Yeah, okay. So, and this is one example of estimation. So we formulate this by the logistic regression. Then we got the estimate of beta naught is equal to negative 10.65 and estimate of beta 1 as the 0.005. So that means the larger balance. And also, sorry, maybe I would say that this is the standard error of beta I hat. And this Z statistic is the beta I hat. Beta I hat over standard error of beta I hat. And this is p-value. So basically the probability that not probability, the p-value. So p-value of for the test that the beta I is equal to 0. So standard error is obtained by the Fisher information matrix. So we have some analytical way to calculate the standard error of beta I hat. And this is just ratio. And one thing you can notice is that this is Z statistic rather than T statistic. Because in linear regression, this ratio follows T distribution. So that's why we say T statistic. But here, everything is by asymptotic theory. And we don't really have any reason that this approaches to T distribution. So this is actually this follows T distribution. So we can only say that this is approximately the normal 0, 1. So that's why that we say Z statistic. Yeah, anyway, for T statistic, if degrees of freedom is large, then it approaches to normal distribution. So if sample size is large, the results are the same. But sample size is small, actually that we don't have better approximation than normal distribution. In linear regression, the T distribution is more exact distribution. But here we only have this approximation. And you can see that these Z values are really large in absolute value. P values are really small. So that means that these are significant. You can see coefficients are much larger than standard error in absolute value. Yeah, and this is by the some iterated algorithm. Like maybe you can imagine Newton-Raphson method. And convergence is good, but still often we have to compute the 3 or 4 times for 3 or 4 iterations of algorithm. But in today's computer, it's very quick, within a second. Yeah. And in the same way as linear regression, that we can calculate the fitted value. So given the beta naught and beta 1 hat, and if we observe new observation x naught, we can maybe this should be x naught. So we can calculate the probability of y naught is equal to 1 given x0. So that is given by this. So fitted value. Fitted value or fitted probability. Yeah, so if we give, okay, so these are our estimate. So for example, if we give 1,000 as the balance of a new person, then default probability is given by this quantity. So this becomes 0.00576. So 0.576%. That is, I think, relatively low risk for low risk to default. Yeah, so we can do it in a similar way as linear regression. So yeah, later we study our code for this, but for example, the fitted values of this logistic regression gives this probability. And the qualitative predictor. So in linear regression, if X is categorical, it does not really matter. We can do some hot encoding. We can, use dummy variables. So we can use the just indicate a variable for each category of the categorical variable. So we can do the same thing for logistic regression. So when X is a qualitative predictor, still logistic regression models works in the same way. So this is one example. So that we fit the default probability by the status, whether the individual is student or not. And here is the result. So what this means, okay, so at first coefficients are here, standard deviation here, Z statistic here, and the p-values are small. So we can say this is significant. So that means this coefficient is positive at least. So that means if a person is a student, then the default probability is higher. And you can compare that in this way. So if student, the default probability is calculated by this, and that is 4.3%. If not a student, then probability is 2.9%. So 1.4% difference between two. Yeah. Do you think it's reasonable estimation results? When I was a graduate student, the one recruiter visited campus from Capital One. Capital One is a large credit card issuer, and that guy said the students have relatively low risk for default because sometimes maybe parents pay off, and also students don't expect that they earn a lot of money. So compared to high income individual who lose a job, maybe the default probability is lower. And also the profile is generally good. For example, the educational level is higher, so students have lower risk. So, but here the students have higher default risk, maybe because we didn't consider other factors. So if we have income variable in this model, if two people, one is student, the other is not student, and they have the same income, probably the students have lower risk for default. So the sign, of course, depends on existence of other predictors in the model. Yeah, any other questions? And next one is multinomial logistic regression. So just the linear regression becomes multinomial in this way. So we have the multiple parameters. And yeah, it sounds estimation becomes much more complicated because parameter space has a higher dimension. But actually this logistic regression, the parameters actually function. Yeah, likelihood function is actually concave. So just images like this. So actually, it's not really difficult to optimize it. So just the first one, and you can use some Newton-Raphson method and so on. So concave function. So the computation isn't really difficult, even if maybe 5 or 10 parameters in this model. Maybe hundreds of parameters, maybe it takes a little more time. Maybe estimation is unstable. So we can see the regression results here. And you can see the student have negative coefficient here. So actually the given balance and income, if these conditions are the same, students have lower probability of default, and it's significant. Balance matters, income doesn't matter. Intercept, usually people don't care. This is just adjustment term. So overall, default risk is lower than beta naught is lower. So beta naught is a kind of business condition in the entire society. Yeah, and how to present logistic regression results. So this is binary outcome. So it's slightly more inconvenient to represent the graph. So for example, how to show the difference for students and non-students in terms of default probability. And here is the graph. So credit card balance. And this is the default probability. And the red one is this, I think the non-student, sorry, the red one is student and the blue one is non-student. So given the same credit card balance, then student have smaller default probability. Yeah, but this kind of graph is a little bit complicated to make because so what happens for the other variable, income? It's not clear. Actually, it's even not clear in the textbook. Maybe they substitute the average income. So, okay, so the original function is here, right? So we make the two graphs. The one is the student status is 0, the other is 1. And the balance is variable, so that's fine. So how about income? It's not clear. Maybe they imputed the average value of entire population. But students have different income levels. So it's not exactly clear what they did in this graph. So this is the credit balance, and this is student status. So if student, the credit balance is actually higher. So if the balance is the same, actually the students have lower default rate. So we have to be careful about the interaction of two variables, right? Yeah, always, people only look at the very limited amount of data, right? So this is political, but for example, think about the equality in the employment, white and African American, and also the male and the female. And okay, so in some occupations, more male than female, and more white than black compared to the population ratio. Then, okay, so less African American, less female. So we hire the African American female. But actually, the most underrepresented group is the African male. I mean, the African American male. So we only see the marginal distribution of race and the marginal distribution of gender. So that sometimes miss some information. So here it's the same thing. So if we only focus on one variable, we cannot really see what happens. Yeah, and the diagnosis, yeah, so in linear regression, we do the residual plots, right? So that we have observations and fitted line, and we can observe residuals, and we can see the residual plots. So here is X, and here is residual, and maybe the sum positive and the negative, negative, positive, negative, and we see this as this has a meaningful pattern or not. And if we have some specific pattern, then basically we can get more information from X. If we add, for example, X squared in the model, or we change X into the log of X, then maybe the model gets better. But logistic regression, this strategy basically does not work. So maybe the stat 6840 covers that, but that is, I think, a kind of the too complicated issue. So in logistic regression, we have X and Y values are all 0 and 1. And what happens? All observations are on this line or this line. So just the densities are different, but basically all points are on y is equal to 1 or y is equal to 0. Then, okay, so we fit this line, we fit the curve, and we see these residuals. And you can see that this residual just replicates logistic curve. So if we think about X and residual, what happens? Then these are positive residuals. So what will happen is that we have this kind of residuals, and also the other way around. You can see the red residuals here. So these residuals like this. So just we replicate the two logistic curves. So this is just a kind of the complement of this curve, and this is also complement of this curve. So just this curve replicated. Maybe density have some information, but except for that, the residual plot itself does not make sense. So if we group these observations, it may make some sense. That was done in 6840, but usually the residual plots are not analyzed. So that means that we just assume that the logistic curve is correct. And actually that's the thing that we do. Yes. So basically, we don't really care about the shape of this, fitted curve. That is just the usual tradition of the binary regression analysis. Yeah, and this is a different issue, but the estimation is pretty good. I mean, it converges first because the beta, the likelihood function is concave in terms of beta naught and beta 1. Okay. And yeah. And next one is the multinomial logistic regression. So how about what to do if we have multiple categories? So suppose we have the classes 1 to k, and we don't have any order between these k classes. How to classify observations, how to predict the class of the observations. And that is, okay, so basically we want to predict these k values, probability of y is equal to 1 to probability of y is equal to k, given x value. And the strategy is we think about the ratio of 1 to k, 2 to k, 3 to k, up to k minus k to k. Then basically it clarifies all probabilities. And at first, for each pair that we consider that this is modeled by this linear function of x1 to xp. And also other pairs, the other pairs are modeled by the same thing. So just the different parameters. So we have many parameters, right? So for example, let's assume that k is equal to 10. Okay, and we have the maybe 3 predictors here. Here, P does not include intercept, so plus intercept, I would say. Then how many parameters in this model? We have so many, right? So we have k is equal to 10. So y is equal to 1 to y is equal to 9. So we have model 1, 2, 3, and up to 9. So this model includes basically 9 submodels. And for each of these 9 models, how many parameters? P is equal to 3, so we have 4 parameters. Okay? And 4 parameters for each model. So in total, how many? 9 times 4, 36 parameters. So we have many parameters in this model. We have a quiz related to this. And this is a natural extension of logistic regression. So remember that the log odds ratio is equal to beta naught plus beta 1x, or in general, up to beta p xp. And this is the probability of y is equal to 1 given x, and this is probability of y is equal to 0 given x. So this is just exactly the same as the previous case. Just k is, the last class is 0, and otherwise it's the same. So if special case of k is equal to 2, and we consider just class 1 and class 0, then this is just the exactly special case of the multinomial logistic regression. Yeah, so, and total probability should be 1. So actually those k minus 1 models are sufficient to identify the probabilities. Right? So yeah. So think about this. So we have the 10 categories, maybe 10 categories too much. So maybe I would say that, sorry. It's hard to manage it. It's sometimes inconvenient. Okay. Just I want to have the numeric example of this. Yeah. So for example, suppose that we have k is equal to 3, and p does not really matter, and the log of something. So log of the p of the y is equal to 2 over p is y P of y is equal to 0, and we got also the log of P of y equal 1 over P of y is equal to 0. And suppose these are the log of maybe 2, and this is log of 3. Then you can see that the P of y is equal to 2 to P of y is equal to 0 is equal to 2 to 1, and P of y is equal to, sorry, yeah, that's right. P of y equal to 1 to P of y is equal to 0 is equal to 3 to 1. So that means this is 1 to 2 to 3. So in total 6, but the 6 should be 1. So that means P of y is equal to 0 is 1 over 6, and P of y is equal to 1 is equal to 3 over 6, and the P of y is equal to 2 is 2 over 6. So based on these two models, we can identify all three probabilities. Yeah, sorry for the terrible writing, but yeah, that is what this multinomial logistic regression do. Yeah, and the multinomial logistic regression is done by multinomial function in NNet package in R. The NNet stands for neural net, and the neural network is multiple layers of logistic regression. So that's why this is in neural net package. NNet package is pretty old package. These days, people are using different packages for neural network. Yeah. And the last one is ordered logistic regression. Yeah, so if a response variable y have more than 2 categories which are ordered, we can use so-called ordered logistic regression. So it has more prior information about categories. So it does not give probability of y is equal to I anymore, but they can project the corresponding class y is equal to I are conditional on x. So yeah, so that's the case. So yeah, and this is in the POLR function in mass package in R. So the basic idea is like this. So we consider, okay, suppose k is equal to 3, and we have the 3 classes 1, 2, 3. And we give the some probability from the model. So some probability. So some p is equal to, say, the f of beta naught plus beta 1x or something like that. Then when the p is equal to, for example, if p is equal to 0 to 0.5, then we categorize this into class is 1, and if p is in 0.5 to 0.7, we predict the class is 2, and if p is more than 0.7, maybe the one of these should be included, but then we categorize this as 3, something like that. So basically, we have just the same predictor and the same model, and based on the score that we judge the class. So if p is less than 0.5, class 1, between 0.5 and 0.7, class 2, 0.7 to 1, 3. So in some sense, it's good because we consider the prior information about the ordered variable. So 1 is closer to 2, but not close to class 3. But on the other hand, this estimation is probably very tricky because we have to decide these thresholds. Right? And deciding thresholds are really nonlinear problem, and usually it's hard to estimate it. So I think we can imagine that this is complicated model. Yeah, but at least it makes sense that we calculate some score, and based on score, we decide the order. Yeah, okay, so that's it for today. And I think I finished most of the logistic regression the slides. So yeah, so if you have questions, you can ask, and otherwise, see you next week.